Let's see. We do have a problem set due next week. I'm going out of town this afternoon, so I won't be around the rest of the week. But if you have any questions, you should email me, and I'll do my best to answer questions before our problem session next week on Monday. All right. Last time we were discussing that although in most of the standard textbooks that discuss time-dependent evolution in quantum mechanics tends to focus on Fermi's golden rule. So we think about there's energy levels, and then we have transitions between energy levels. And there's rates of population moving between levels. That population rate is given typically by Fermi's golden rule. But that really doesn't tell the whole story. That is an appropriate regime, as we'll see, when we think about the processes of transfer of population between these different levels as kind of incoherent processes. But we know in quantum mechanics that we have generally continuous time evolution of probability amplitude. And the transition between that picture of thinking about unitary evolution with a continuous rotation of sorts in Hilbert space, probability amplitude moving between different states within the Hilbert space. That to a picture in which we think about this that's not really kind of describable by a unitary evolution anymore. That's a very subtle and difficult problem. And in some ways still contentious. I mean, it's as contentious maybe as the similar problem in classical physics when we think about the Hamilton's equations of motions classically. They are reversible trajectories, whereas thermodynamics involves irreversible processes. So the transition, how we think about fundamental equations that are time reversible to some effective description in which things are irreversible, that's a subtle and difficult problem. We have some ways of understanding that and some effective theories, but I would say there's still, how we fundamentally reconcile that still is a problem for study. With all of that sort of background said, we turned our attention, we said, let's think about now a circumstance in which we're applying something like a laser field or an RF generator or a microwave form, and we have a coherent oscillation of our electromagnetic radiation that's oscillating at some frequency, and that frequency is tuned near to resonance with two levels, okay? And so that there is going to be resonant phenomenon, and that resonance then dominates over all other dynamics. And to the degree to which we think about this system as isolated and not interacting with the environment at all, then this is essentially the whole system is restricted to these two levels. Okay. So we have then, in some sense, a very simple, if not trivial, quantum mechanics problem to solve the time evolution. We solve the time-dependent Schrödinger equation for the problem of these two levels, driven by some interaction Hamiltonian. So all the complications of our atom regarding, closed shells and Hartree-Fock and blah, blah, blah is reduced to this Hamiltonian. Okay? We got two levels. One we call the ground state and one we call the excited state. And we can choose the zero of energy is irrelevant, so we're going to take the ground state energy to be zero. And then the excited state energy is equal to the resonance frequency, which is the difference in these energies, which can be written as h bar omega Eg being the Bohr frequency. And our interaction, for the moment, we take this, we imagine this to be a dipole-allowed transition, but it could also be a magnetic dipole-allowed transition or a quadrupole transition. Doesn't really matter. The same basic description applies. It's just there'll be a different coupling matrix element between the two states. And we have some complex amplitude, which may depend on the position of the atom, and it's oscillating at the frequency of what we'll call the laser. And again, when restricted to this two-level system, we find this interacting Hamiltonian reduces again to a very simple form. It has only off-diagonal matrix elements, ones that can connect us between the ground and excited state, either raising or lowering the system between the ground and excited state. Okay? And the coupling strength, this energy, is written as h bar capital omega, where that strength depends on d dot e, where d is the dipole matrix element here, and E is the amplitude of the electric field that's polarized in some way. And this frequency, we said, we call the Rabi frequency. Okay? So this is a simple problem. We then set up and we just solve the time-dependent Schrödinger equation, restricting it so we want to solve for the probability amplitudes in these two levels as a function of time. And that was something that, in general, there is no exact solution to this ODE. Because it is an ODE with time-dependent coefficients. And generally, those equations are not integrable. However, this problem is approximately integral when we have the situation that the detuning here, which is defined as the difference between the applied frequency and the resonance frequency, if the detuning, or the magnitude of the detuning, and the Rabi frequency are much, much less than the resonance frequency, then we were able to transform this equation in such a way that we can approximately solve it. And the approximation is better and better the smaller and smaller these quantities are compared to the resonance frequency. So the way we did that is we said we went to something we call the rotating frame, and we'll explain that in a little bit more detail today. But I wanted to review all of this stuff again in detail because it's very important. So once we made this transformation, we then were able to essentially time average this set of ODEs over the period of oscillation, and the rapidly oscillating terms then average to zero. They don't contribute to the evolution. And we end up with then a matrix equation or a set of ODEs which involve a time-independent Hamiltonian matrix in the rotating frame, in the rotating wave approximation. And that matrix is the representation of this operator. Okay? And that set of ODEs we could solve. And so, in particular, we looked at the solution for the case where I was exactly on resonance, where the detuning was 0, and then I started in the ground state. And in that particular case, we found this solution for the probability amplitudes as a function of time, and they oscillate. And therefore, the probability, say, to be in the excited state, which is the square of this amplitude, oscillates. And it oscillates at the Rabi frequency. Okay? So, to the degree to which this is a good description, what we see is that when we apply a coherent drive that is resonant, or generally near resonant, as we'll see, with our two-level system, then the effect is not just to have random jumps from ground to excited, but we have a continuous oscillation of probability amplitude between the two states with an oscillation frequency that depends on how strongly the field and the system are coupled as described by the amplitude and the appropriate coupling matrix. Okay? So, the thing we also discussed at the latter part of the lecture yesterday, or Monday, whatever the heck that was a useful picture for understanding these kinds of quantum dynamics, because we have restricted ourselves to a two-level atom. So all of our atomic physics is buried in there, the structure. Then this has a complete mapping, one-to-one, as far as the mathematics is concerned, with the dynamics of a spin one-half particle. So again, it's nothing to do with the spin of the electron. It's just a mapping, because all two-dimensional Hilbert spaces are the same. It doesn't matter what I call up and down. I could just do a mapping. Call spin up, call that the excited state, and call spin down the ground state. So then every state of a spin one-half particle corresponds to spin up along some direction. So spin up along x is a superposition of spin up and spin down along z, etc., etc. So we have a sphere here. If I were to think about this as a spin, then there is a isomorphism between the Hilbert space of a spin and a sphere. Oh God, I hope Deutsch, you cannot draw perspective. All right. So, this is spin up, and I'll just, for emphasis, call that spin up along z. And this is spin down along z. So in the Hilbert space, the antipodes are orthogonal states, because this is not real vector space. This is Hilbert space. Okay? And Hilbert space is this complex vector space, but that complex vector space maps onto the surface of the sphere. And then let's call this spin up along x. This is spin down along x. Well, the way I've drawn this, then this is spin down along y. And this is spin up along y. And every one of those states, and spin up along any other direction, is some superposition of spin up and spin down along z. The thing about the states in the equator is that they are equal superpositions of spin up and spin down. What distinguishes them is the phase. So for example, spin up along x is equal to spin up along z plus spin down along z with a probability amplitude of √2 in each case. But spin up along y is spin up along z plus I times spin down along z with √2. So they are both 50-50 probability of being spin up and spin down. But what distinguishes these two states, which are not orthogonal states, but states that are not equal, is, I'm sorry, what am I saying? Is it Chris Arnold? No, sorry, never mind. But what distinguishes these two states is the phase. So this picture is isomorphic to the sphere, where we make this mapping, and then we just go one-to-one map. This state then is E plus G over √2. And this state over here is E minus G over √2. And this state here is E minus I G over √2. And this state here is E plus I over √2. And states that are elsewhere, not on the equator, are going to be not equal superpositions. This one's going to be much more, have a higher probability of being excited than ground. And this state would have a higher probability amplitude being more ground. I mean, more generally, I can write this as some cosine theta over 2 E plus I e to I phi cosine, I'm sorry, sine theta over 2g, where this is spin up along the direction theta phi. So if I specify a spin by polar angles theta and phi, then that corresponds to some combination of the spin up and spin down, and that would be some arbitrary state. And this is known as the Bloch sphere. Now, the dynamics of a spin 1/2 particle, as generated by whatever Hamiltonian we have, there's only one dynamical thing as far as Hamiltonian dynamics are concerned. There's only one thing that can happen to a spin 1/2 particle. It can rotate. It can point from spin up along some direction to spin up along some other direction. Because we just said every state of a spin 1/2 particle is spin up along some direction. So if there's going to be dynamics, all it's doing is rotating. It's a rotation matrix on a two-dimensional Hilbert space, which is a matrix in the group SU2. So in this case, we have such an example. We see that here. If I now make this analogy and make this mapping, then the operators that act on my two-level atom are operators that can be written in terms of, oh, I shouldn't have quickly erased that, but we got it. So in this case, then we make the mapping of operators acting on my two-level atom, they all could be mapped. Every operator is some amount of the identity, sigma x, sigma y, and sigma z. Those are the only possible operators, or some linear combination of them. Because all 2x2 matrices can be expanded as some amount of sigma x, sigma y, and sigma z in the identity. So for example, spin up, spin down, or as we had in the excitation operator associated with our Hamiltonian, that excitation in this mapping takes spin down to spin up, which we call sigma plus, and vice versa. Whereas, say, if I looked at the projection operator onto the excited state, that maps onto, in this spin analogy, up, up. But up, up is the projector, which is a linear combination of the identity and sigma z. Because sigma z is that matrix, right? It's the matrix with is diagonal with eigenvalues plus or minus 1 in the standard basis. By the way, if I don't put the little x, y, or z on it, I'm treating it as a standard basis, the z eigenstates. And then say sigma x is equal to sigma plus sigma minus, which is 0, 1, 1. And sigma y is sigma plus sigma minus over I, which is minus I, 0, 0. Okay? So, with that analogy, we had in the rotating frame well, actually, before I go, why the heck is it called the rotating frame? Well, that is now understandable in thinking about the dynamics on the Bloch sphere. So, our Hamiltonian, before we made the rotating wave approximation, was h bar, maybe eg plus where I took the phase to be 0. Okay.
That should be EE on that first term.
Thank you. Right. So, with this analogy that we just made, this is equal to h omega eg over 2 times the identity plus h bar omega eg over 2 sigma z plus h bar omega cosine omega t sigma plus sigma minus, which we just said was equal to sigma x. Okay? So, what does this mean? Well, if I think about this, remember, of course, that if I think about a rotation matrix, or the rotation operator, in 2D Hilbert space. I have the rotation matrix is rotation about some axis, let me call it E sub n, by some angle, and the angular momentum vector over h bar is sigma over 2. Okay? And this then is cosine theta over 2, 1 minus I sine theta over 2, the direction E sub n dotted into the vector of all sigma matrices. Something you remember from your quantum mechanics. So, what we have here is a Hamiltonian that is a generator of rotations, right? Because if I exponentiate this Hamiltonian, it's going to be of this form. Of course, it's going to have time-dependent stuff and how the fact that we couldn't just exponentiate it and solve for the time evolution operator because we had these time-dependent coefficients, and because sigma x and sigma z don't commute at different times, we have different sigma matrices and they don't commute. So the Hamiltonian doesn't commute with itself at different times. And therefore, you can't just exponentiate the Hamiltonian. You have to have the time-ordered product and the Dyson series and et cetera, et cetera. But we can get a little bit of a physical picture of what's going on. This is the standard picture of what's called spin magnetic resonance, which is NMR. In spin magnetic resonance, what you do is you put on a big magnetic field in the z direction. So, you put your head in that big MRI machine. It's got a big magnet in it. Your protons in your water, most of your body, then start spinning around. So here's my big magnetic field, and loosely there's some, spin here, and it starts precessing. Now, what is then done to drive transitions from spin up to spin down is if I put on a tiny static magnetic field here, nothing's going to happen, right? Because it's going to be so small, it's going to slightly rotate this magnetic field, but it just keeps spinning like that. On the other hand, if I put this tiny magnetic field on, let me call this B parallel, B perp, and I oscillate it, well then, I have resonance. Remember, there's a resonance frequency here, called omega naught, which depends on the gyromagnetic ratio and the strength of the magnetic field. If this thing starts oscillating at that same frequency, well then there's going to be resonant phenomena. However, this spin is going around in a rotating frame, whereas this thing is going linearly. So, I can break up my linear oscillation into two pieces. One that's co-rotating with the spin, and one that's counter-rotating. The one that's co-rotating with this precession is such that it's the torque of this transverse field that's induced on this gyroscope is constantly going to be adding up. And this thing is then going to start precessing around around this vector, because it's always in phase with it. And therefore it will flip, even if this is a tiny frequency. And the frequency at which it will flip is the frequency associated with this transverse field. So we go to the rotating frame by transforming into the frame co-rotating with this free evolution. And then we will see that there is a term in the perturbation that is co-rotating, that adds up, and a term that's counter-rotating, that basically it's going the wrong direction and can never add up in a resonant way. Well, that's exactly what this picture is. This is my bias magnetic field, which gives us, this is a big energy associated with the splitting between the two levels, E and G, that gives that big bias. And then we apply this tiny magnetic field because this frequency is assumed to be small compared to that. But it's oscillating in the x direction. We can break that up into a piece that's oscillating e to the co-rotating and a piece that's counter-rotating. And the rotating wave approximation then is as long as this precession frequency is much smaller than this precession frequency, then I can neglect the counter-rotating term. And that's where the term rotating frame and rotating wave approximation comes from. Okay? So, another lesson that we learned from studying this is that the problem of Rabi oscillations is the same as spin magnetic resonance. They're one and the same as far as, I mean, that's the beauty of physics. We have a mathematical description that is universal, that describes many different things. In one thing, we're talking about protons spinning around in a magnetic field. In the other case, we're talking about electrons moving to different orbitals. But the physics, as far as we're concerned, is the same physics. It's just coherent coupling of two eigenstates by an oscillating drive that's oscillating near resonance with those two levels. That's pretty neat, I think. Okay, so, yes, do you have a question? No.
Well, sort of. If you detune enough from resonance, the counter-rotating term is important. Are there any interesting dynamics there, or is it really only interesting if you up your Rabi rate enough that?
No. Well, if you detune way far, then as we see in the homework, as we'll discuss maybe a little bit either today or next week, then of course I can think about that as giving an effective energy level shift to the system, which meant if I applied yet another applied field, it would be resonant at a different frequency because I would get a level shift. It's only when if I start cranking up this field to be on the order of this, then I get so-called Bloch-Sphere shifts.
When we calculate the light shift, though, isn't that in the rotating wave approximation?
It is, but we can, that is for sure true. I mean, if I want to talk about the breakdown of the rotating wave approximation, I can do that in two different ways. I can either detune very, very, very large, when my detuning gets to be on the order of this frequency. Or I can crank up the power more and more and more and more. And I think the main effect of that, to the degree, for the case that this is really spin 1/2, is a Bloch-Sphere shift. That's pretty much it. On the other hand, if we're talking about an atom, where I really have more than two levels, well then if I start detuning very, very far, well then I start, the two-level approximation is just already a bad approximation. And then, then it becomes a much more complicated dynamic than a two-level system. Right. So, because of this analogy with spin resonance, we can think about the solution to the Rabi problem as just a rotation on the Bloch sphere. So in the rotating frame, in the rotating wave approximation, my Hamiltonian then took the following form. Where I've neglected the identity term because it does the same thing to the two levels, and that doesn't drive any dynamics. So the solution in the rotating frame, in this case, I could just exponentiate the Hamiltonian because the Hamiltonian is time independent. And that is equal then to what? Well, let's look at the case first that we just looked at, where delta is 0. When delta is 0, then this is just given by that. That factor of 2, by the way, came from the fact that half of the power was co-rotating and half of the power was anti-rotating, counter-rotating. So that's why, remember we had omega and then we turned to an omega over 2. Is equal to e to the minus I sigma x over 2 times t. Which is a rotation around the x-axis. In this case, it's around the negative x-axis because of my conventions. By the way, word of warning. The sign convention of the Rabi frequency sometimes gets screwed up. And Chris Foot does that, and it pisses me off, but sorry, Chris. But remember, we define the Rabi frequency as d dot e. So I have this, end up with this minus sign because the interaction strength is minus d dot e. Whereas sometimes you will see it defined as the charge of the electron times which is minus my definition. Just as a way of absorbing this minus sign. I mean, there's one convention or the other, but I hate dragging that extra minus sign around. It's too many minus signs to. So just note, if you're looking at the textbook, all the omegas have the opposite sign convention. You should look at the textbook. Okay, so, right. So this is the solution. So this is the case that we just had. If I started, if my system started in the ground state, then at a later time, we have cosine omega t over 2 times the ground plus I sine omega t over 2, and sigma x acting on the ground state is the excited state. Is that sigma plus sigma minus. And that's the solution that we wrote down, where the probability amplitude in the ground state oscillates like this in the pop. And we recognize that as just a rotation on the Bloch sphere. So we started in the ground state, we have a torque vector in the minus x direction, and the spin precesses. I was supposed to get to the North Pole, visit Santa, come back, and do that. And those are our Rabi oscillations oscillating at this frequency, right? Now, as we discussed last time, if I time this very well, if my time is such that omega t is equal to pi, then this is 0 and this is 1. And this is the excited state. I mean, the overall phase is irrelevant. So this is what is called a pi pulse. A pi pulse is a pulse of the electromagnetic radiation whose power is chosen, because remember, the Rabi frequency depends on the amplitude of the field, such that, and for the given coupling matrix element, the time is such that that power is on for a time such that omega t is pi. And then we would invert the system. It would go from the ground state to excited state.
So you can really switch it on and off of that fast?
How fast is fast? Well, it depends how big omega is. Okay? So remember what we just said is omega, the stuff I just erased, omega dependent is d dot e. So the question really is, how much power do you have? So this is not the Bohr frequency, right? This is not, 1 attosecond pulse. This is the frequency associated with, h bar omega times this, excuse me, that energy. So it really depends on how big is the dipole matrix element and how intense is your laser beam. And, sort of a good coherent field on an optical transition with high oscillator strain. This is maybe, 100 kilohertz, few megahertz. So that's pretty easy to do. As we also discussed, if I set it the time half as long, then the state at this time is what? Well, this is then equal to cosine plus I e over root 2, or e plus or minus I g over root 2 times an overall phase of I. So a pi over 2 pulse is a pulse that takes the system, if it's, say, started into a ground state, into the equator. And in particular, it takes it over here. This is a rotation by pi over 2 on the Bloch sphere. And that point is an equal superposition of ground and excited with that particular phase. This is the one we said to spin down along y, which is exactly what it should be in this case. So a pi over 2 pulse is a pulse that creates an equal superposition of the two levels, assuming that I started in one of the eigenstates. All right. What about let's see, what do I want to say? Oh, I guess maybe I'll say one other point here. suppose I chose this phase to be 0. What if I chose the phase to be something else? So I do this first pi/2 pulse, I get it over here. Now I'm going to apply a second pulse, but I phase shift. I put a phase shifter which shifts the phase of the oscillation by some amount. How does that affect the dynamics? So if I had the phase differently, I would have had this as cosine something like that. Well, if I think about that going to the rotating frame, that's equivalent to an oscillation, since it's phase shifted. Remember, my spin was precessing around the big magnetic field. If I phase shift my applied radiation, then it's going to be out of phase. It's going to be rotating around the same frequency, but it's going to be out of phase, which is equivalent to just moving the torque vector, so that I'm no longer torquing around the x-axis, but I'm torquing around some other axis in the equator. So if I apply my first pulse along this axis, and then I applied my second torque around that axis, I would bring it back down to the ground state. Whereas I put the torque around here, the second time I bring it up, if I did 2 sequential pi/2 pulses. So the phase of the oscillation determines something about the direction of the torque vector of the pseudospin on the Bloch sphere. What about the detuning? We set the detuning to 0. What if the detuning were not 0? Well, we have the solution. Because this is the Hamiltonian, we just have to exponentiate it. So, for detuning not equal to 0, or more general, the time evolution operator, which is this, is equal to what? It's equal to e to the I delta sigma z plus omega sigma x over 2. Now, that looks a little bit more complicated, but in fact, it is of this form. Because it's some vector, I'll write it as e to the I over 2 omega effective dotted into sigma, where omega effective is a vector whose x component is the Rabi frequency, well, it's the negative of this. If I take this vector and dot it into the vector of sigma matrices, I get that. So what is this? Well, this is a rotation. I should say omega t. There's a time here. Excuse me, that's missing. What is this? This is a rotation operator that rotates by an angle depending on the magnitude of the omega effective, which is the square root of omega squared plus delta squared. That's the magnitude of that vector. And the direction of the rotation is the direction of this vector, which is the unit vector. So it's minus omega over omega effective in the x direction, minus delta over omega effective in the z direction. Let's write it out. Well, before we write it out, we can look instantly on the Bloch sphere and understand what we expect. What do we expect? Well, the torque vector is now tilted because now it has a z component. Okay? Let's say the detuning were positive. Then it's tilted down. And the torque vector is made bigger. It's made bigger by an amount depending on delta. That's to say the magnitude. So, whereas before, when we were on resonance, we oscillated along this great circle that connected the north and south pole. Now we oscillate along this great circle, torquing around the system. And we oscillate faster because the torque vector has a bigger magnitude. So what do we see from this picture, if we can understand? What we see is that, firstly, we oscillate faster between these two states. Moreover, we never get, with unit probability, into the excited state. And the bigger the detuning, the bigger the detuning, the more I torque this torque vector is closer and closer to the z-axis. If I had a huge detuning, then I oscillate pretty much and stay in the ground state the whole time. So if I'm detuned very far from resonance, we don't expect to excite the system. There's some tiny probability amplitude, depending on the detuning, to get to the excited state. But it generally just oscillates very close to the ground state. So we can see a formal general solution to that by writing out this rotation matrix, which is cosine omega effective over 2, which is sometimes known as the generalized Rabi frequency times the identity plus I sine omega effective. Well, I guess I defined the negative sign in the direction, so I'll leave it at there. Minus sine E sub n dot sigma, which is equal to, this is equal to minus omega over omega effective sigma x minus delta over omega effective sigma z. So we can now look at the general solution for Rabi oscillation, at least for an arbitrary detuning, an arbitrary Rabi frequency within the rotating wave approximation. Assuming at time t equals 0, I started in the ground state. That is equal to, well, the identity acting on the ground state is the ground state. Sigma x on the ground state is the excited state. Sigma z on the ground state is minus the ground state because g is like spin down. And sigma z acting on spin down is minus spin down. So what I get is cos omega effective over 2t minus sine, minus sine, minus sine. I hate minus signs. Times delta over omega effective t plus I effective sine omega effective over 2 times t sine. This is the general solution of Rabi oscillations. So, from this we can see what this, I mean, we could have done it many ways. We could have just done it from geometry, just thinking about an equilateral triangle or whatever, is, you know, what's the projection on this thing. But we got the solution here. Says that the probability to be the excited state as a function of time, given it started in the ground state with this Rabi oscillation, is omega squared over omega squared plus delta squared times the sine of the square root So what this says is that what we showed then is that if I'm on resonance, I oscillate all the way. Why do I keep drawing these things bad? From the ground back to the excited ground, etc. Whereas, so this is for the case where I'm on resonance, where the detuning were 0. If the detuning is not 0, then I start oscillating faster, and the peak probability to, if I started in the excited state, if I started in the ground state, never gets very big. Depends how big the detuning is compared to omega. Okay? When the detuning is really big compared to delta, compared to omega, well then this is tiny. It's essentially 0. And almost all the population stays in the ground state. I mean, if I were to look at the population in the ground state as a function of time, it would be 1 minus this, and this is 1. like that. So in that circumstance, when the detuning is big, and big means that it's large compared to the Rabi frequency, then the picture we have is no longer one of Rabi oscillations, but one more of level shifts. Now this is a little bit of a different kind of level shift than perhaps you used to think about, where we do typically time-independent perturbation theory. We add in a perturbation Hamiltonian, and then we rediagonalize the Hamiltonian and we get new eigenlevels, new eigenstates. Here, we're driving the system time-dependently, which typically we think about as driving populations between the states. But when that driving is not close to resonance, and not close means this, then there's very little probability that moves from one state to another. Instead, we end up oscillating the probability amplitudes. And that oscillation, we know, if I think about an energy, if I think that about some probability amplitude as a function of time, as being some level alpha. If it were an eigenstate, it would just have some oscillation of the probability amplitude. If the effect of my perturbation is essentially to add an additional oscillation, well, that's equivalent to adding like a little extra energy shift to the system. And you're solving for that in homework. That's what we call the light shift. Also known as the AC start shift. Also known as the dress states. So the dress states are the eigenstates of the atom, including the interaction. We think about the atoms as being bare and naked when they don't have any photons around, and then they get those photons and they're nicely dressed. So we talk about the bare states and the dress states. So our bare states were these particular levels. When we put on the light, what we find is dress states. And so we end up with a shift in these levels. Which goes in the, so this is what we'll call the light shift. They shift in opposite directions, and whether it shifts up or the other way around, where the ground state now shifts up and the excited state shifts down, depends on the detuning. The light shift is equal to h bar omega squared over 4 delta squared. For now, that's what it is. No, that's not correct. No square, it's important. So the light shift, this is the light shift on the ground state. What we see is that when delta is less than 0, then, which is what we call red detuning. Remember, delta is the applied frequency minus the resonance frequency. So delta being negative means that I am detuned below resonance. The ground state energy is shifted down. if, on the other hand, I had blue detuning, then the opposite is true. The excited state level is shifted up relative to the bare state, and the excited state is shifted down. Now, a way to understand this is, as you will explore in your homework assignment, is to think about the dress states and the shifts and the light shifts in terms of the AC Stark effect. So remember the Stark effect. When we talked about the DC Stark effect, we had the atomic Hamiltonian, and then we had a minus d dot d, where E was static. And what we said was, if we started in a system which, like an atom which, or in an eigenstate of the atom which has no preferred direction, it's an eigenstate of parity, and therefore has no dipole moment, then the effect of the interaction was first to induce a dipole moment. So we have this picture of, the ground state of hydrogen or some alkali with an s orbital. We apply a DC electric field. That DC electric field, if this is the positive charge, separated positive and negative charge. Goes the other way around, of course. Inducing a dipole moment. That induced dipole moment to lowest order is proportional to the electric field. That induced dipole moment then interacts with the field to give us an interaction energy, which for an induced dipole moment is minus a half alpha E squared. Shifted the energy down. When we have a time-dependent perturbation, well, now we have resonance. And thinking about this as a charge on a spring, of course, it's isotropic spring, but I'll just draw it like this. So really, there's no direction to start. There's some resonance frequency here. Let me call it like that. Okay? Here's my spring. See it? There's my slinky. Now, I'm going to drive that slinky. I should have brought my slinky in, but you can see it, right? If I drive that slinky, and I drive it below resonance, well, let me do it above resonance first, because that's a lot easier. This was a low resonance. So I'm not going to drive it like this. In steady state, how is this thing going to oscillate? Sorry. So this is the resonance frequency. Now I'm going to drive it faster. Well, what's going to happen is it's going to go 180 degrees out of phase. So if I drive it above resonance, then alpha is negative. If alpha is negative, well, first of all, in this case, the AC Stark effect is going to be equal to minus a quarter alpha E squared. Why? Because of the time averaging. There was an E squared was cosine squared omega t, and then I time average it, which is like the rotating grid approximation. That's where that back and forth comes from. So, if alpha is less than 0, then delta E is positive. That's blue detuning. On the other hand, if I drive it much slower than this frequency, then it stays with me. In which case alpha, in this case, so for red, this is blue detuning. In which case, this is negative. So we can understand the light shift just in thinking about the polarizability of the atom, thinking about it now not in terms of the DC polarizability, but the AC polarizability. That's to say, if I have charges bound on springs, if I drive them, they're going to be induced dipole moments that are oscillating. The size and sign of that oscillation depends on both the size of the drive as well as whether I'm tuning above resonance or below resonance. All right. Very good. Anybody have any questions? All right, well, we'll call it quits for today. And we'll pick it up next time. We'll talk about, next time, we'll need to think again about now, we've ignored spontaneous emission. And we need to put that back into the story to really fully understand and treat the problem. So we'll get to that next time. All right. Let's see. We do have a problem set due next week. I'm going out of town this afternoon, so I won't be around the rest of the week. But if you have any questions, you should email me, and I'll do my best to answer questions before our problem session next week on Monday. All right. Last time we were discussing that although in most of the standard textbooks that discuss time-dependent evolution in quantum mechanics tends to focus on Fermi's golden rule. So we think about there's energy levels, and then we have transitions between energy levels. And there's rates of population moving between levels. That population rate is given typically by Fermi's golden rule. But that really doesn't tell the whole story. That is an appropriate regime, as we'll see, when we think about the processes of transfer of population between these different levels as kind of the time evolution. We solve the time-dependent Schroeder equation for the problem of these two levels, driven by some interaction Hamiltonian. So all the complications of our atom regarding, closed shells and Hartree-Fock and blah, 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 is reduced to this Hamiltonian. Okay, we got two levels. One we call the ground state and one we call the excited state. And we can choose the zero of energy is irrelevant, so we're going to take the ground state energy to be 0. And then the excited state energy is equal to the resonance frequency, which is the difference in these energies, which can be written as h bar omega Eg being the Bohr frequency. And our interaction, for the moment, we take this, we imagine this to be a dipole allowed transition, but it could also be a magnetic dipole allowed transition or a quadrupole transition. Doesn't really matter. The same basic description applies. It's just there'll be a different coupling matrix element between the two states. And we have some complex amplitude, which may depend on the position of the atom, and it's oscillating at the frequency of what we'll call the laser. And again, when restricted to this two-level system, we find this interaction Hamiltonian reduces again to a very simple form. It has only octagonal matrix elements, ones that can connect us between the ground and excited state, either raising or lowering the system between the ground and excited state. Okay? And the coupling strength, this energy is written as h bar capital omega, where that strength depends on d dot e, where d is the dipole matrix element here, and E is the amplitude of the electric field that's polarized in some way. And this frequency, we said we call the Rabi frequency. Okay? So this is a simple problem. We then set up and we just solve the time-dependent Schrödinger equation, restricting it so we want to solve for the probability amplitudes in these two levels as a function of time. And that was something that, in general, there is no exact solution to this ODE. Because it is an ODE with time-dependent coefficients. We have some ways of understanding that and some effective theories, but I would say there's still, how we fundamentally reconcile that still is a problem for study. With all of that sort of background said, we turned our attention, we said, let's think about now a circumstance in which we're applying something like a laser field or an RF generator or microwave form, and we have a coherent oscillation of our electromagnetic radiation that's oscillating at some frequency, and that frequency is tuned near to resonance with two levels, okay? And so that there is going to be resonant phenomenon, and that resonance then dominates over all other dynamics. And to the degree to which we think about this system as isolated and not interacting with the environment at all, then this is essentially the whole system is restricted to these two levels. So we have then, in some sense, a very simple, if not trivial, quantum mechanics problem to solve incoherent processes. But we know in quantum mechanics that we have generally continuous time evolution of probability amplitude. And the transition between that picture of thinking about unitary evolution with a continuous rotation of sorts in Hilbert space, probability amplitude moving between different states within the Hilbert space. That to a picture in which we think about this that's not really kind of describable by a unitary evolution anymore. That's a very subtle and difficult problem. And in some ways, still contentious. I mean, it's as contentious maybe as the similar problem in classical physics when we think about the Hamilton's equations of motions classically. They are reversible trajectories, whereas thermodynamics involves irreversible processes. So the transition, how we think about fundamental equations that are time reversible to some effective description in which things are irreversible, that's a subtle and difficult problem.